Okay, so hi everyone. It's a great pleasure that I can share our proposals, status, and plans for the JSALT 2020. So before I start to share, I guess most people are still stay at home now. So I want to wish everybody is having a happy and safe homestay. So this year is very unique. And we have some arrangement accordingly. I will introduce later. The topic of our plan is a speech recognition and diarization for unsegmented multi-talker recordings with speaker overlaps. It's actually quite a long name, but it's actually targeting very, very common problems we observe daily, which is the far-field conversation speech transcription and diarization. So in other words, the problem we are trying to handle here is very simple. It's happened every day in our lives. Maybe not now the life nowadays because most of our current conversations happen online. But in daily, we will have a meeting and a conversation. We are trying to handle the problems of who speak what at what time. On the scenario of 2 to 8 speakers, and with the overlap ratio between 15 to 25%. And this number is observed from the real meeting data. So human usually don't observe, notice this overlap, but it do exist. And we are trying to process in the unsegmented continuous recordings from the whole meeting session rather than this one single segmented utterance. We are trying to handle the utterance for the observation recordings from the total meeting, which can range from 5 minutes to a couple of hours. And that is recorded from different condition and setup. For example, it could be recorded from a single microphone, or it can record it from a microphone array or multi-microphone array or ad hoc microphone array. So this is actually a very, very frequent happen scenario, but meanwhile, it's a very challenging problem because nowadays most ASR system and diarization system have a single active speaker assumption, which means during training, they are usually trained with only one speaker, activate speaker, because usually the speech overlap is considered as a small ratio. But if we do a little closer look, we can see that even a 10% overlap speech could double the word error rate. For example, if we have a 10% of word rate for the single speaker cases and a 10% overlap speech, so what we will end up with is 19 word error rate. So that's almost double the word error rate. So this is actually pose a very significant problem if we want to minimize the word error rate for the conversation among multiple people. And also, meanwhile, a lot of speech separation is usually made to handle this problem, but that also have a lot of unrealistic assumptions we can observe in different works. I will introduce it in this slide. So in past 5 years, we observed a rapid growing research activities in all the relevant areas, including the speech separation, speaker diarization with overlap handling, multi-talker end-to-end speech recognition. But we observed that a lot of those work, although they made very significant improvement, a lot of unrealistic assumptions are still used in those systems. For example, in most of the speech separation work, they assume that an accurate utterance boundary information is available. So if we imagine in a very long recording from the meeting, we can easily find out that this accurate boundary information is not that easy to obtain, because when we have overlap region, the offset and onset of the utterance is sometimes misleading. So that means if we want to get those information, we need to have this overlap handling capability. So that causes a chicken egg problem. And also in some other works, the speaker number, speaker ID is known beforehand. So which is okay for some particular applications, but maybe in other cases, this assumption will not hold. And finally, for speech overlap condition, we know that in our daily conversations, the overlap speech can never have this fully overlapped utterances. But in the benchmark, such as WSJ02 mix, all the overlapped speech are 100% overlap. So the system built on those data sets will missing one very important factor, is that the separation system should not only separating the mixing speech, but also should not add additional interference for the single speaker region. So that part is also usually ignored by a lot of systems. So when we put that to the real world problem, we found, okay, we will suffer from a lot of those kind of interference. So the proposal here, the motivation for us is that we are trying to build a bridge between the research, state-of-art research, and these real-world app problems. So we can link this very fast growing research activities to a more realistic problem. So we can bridge them two things, so to them benefit from each other. So our proposal is actually pretty simple here. So we have two aspects. Firstly, we want to build and benchmark several fully contained multi-talker transcription systems. And then on top of that, we want to explore end-to-end modeling for dealing with this recording condition and the long recordings. So this year, because we are moving to the virtual collaboration, that gives us opportunity to have more members. So we actually have a very big team this year, and the team is from a very diverse and background. So we have 42 total members with 15 graduate students and 27 researchers. And among those 42 members, we have 21 full-time members, including 13 full-time student members and 8 full-time seniors. And also among these 42 total members, we have 17 from industrial and 25 from academic institutes. And that's totally from 12 sites across 4 continents and 6 time zones. And all the members, we have members from which has very impactful works in different areas, including the speech recognition, diarization, speaker ID, separation, Bayesian modeling, and signal processing. Basically, every area related. So we have some experts, corresponding experts. So that gives us very good opportunity and make us very excited to have this workshop. Even though it's online, we know that for the online workshop, we really suffer from some efficiency in communication. So given we have a long list, I will not read them all. I will just list them here. But anyway, we are very, very excited to have this workshop. So also because of this unique situation, we have virtual collaboration. We have a large number of participants. We have different time zone. So this year, within the team, we decided, after several rounds of discussion, we decided to employ a sub-team parallel development strategy. So we firstly form six sub-teams from a bottom-up manner based on the shared interests. So each of us presents the idea, so we just naturally cluster them end up with 6 clusters. And each cluster we assign at least 1 full-time senior member serving as the point of contact. And also each sub-team working on 2 or 4 individual projects. Of course, a lot of projects have interaction. We will start with this assignment. And because we have different people from different time zone, different sites, and people using different tools. Some people using Cloudy, some people using TensorFlow, some people using PyTorch. So we end up deciding that to keep us as a whole group and to have a maximum transparency and sharing. So we decide to unify the test set and development set, especially during developing stage. So we pick LibreCSS dataset as a shared development set. So no matter what tool people are using, people trying to work on this dataset, I will introduce in more detail in next slides. We are trying to work on the same dataset. So then our results can be shareable, comparable. And remember, we want to build a platform. So we will build we will set up several standard based on this dataset. And also we design our system as a modularized, have a modularized design. So with a unified IO format, so I put a small example on the right-hand side. We can see this is a standard Cloudy style, so you have a different step. So within each step, they can be arbitrary tool. They can be TensorFlow or they can be PyTorch. as long as this I/O is unified, so we can easily inject different modules from other sites or other tools here. So the LibreCSS dataset is the one we pick to use for the 6 weeks development and benchmarking. So it consists of 60 real multi-channel recorded mini sessions from totaling 10 hours from mid-sized meeting room. And the source is replaced, so it is consists of the replayed audio with LibreSpeech test set as a source. So totaling with 40 speaker and 8 speaker per mini session. So we design 6 different overlap ratio and 2 silence lengths for the meeting. The overlap ratio is ranging from 0% to 40%. We're trying to have this different overlap ratio to see what will impact how much it will impact the different systems. Meanwhile, we're also preparing a LibreCSS ad hoc set. So we have even more data from that set. So we have a more like room time. We have small, medium, large, and we have varying speaker numbers in each recording. But sadly, because of the pandemic, the 8 speaker session was not finished. So we only have 2 and 5 now. So we can use that, but we can still evaluate our system on that data set. So based on this LibreCSS data set, we build, before the workshop, we built 4 baseline pipelines that is published in the recent years that have this full stack of the processing pipeline. So which are the CHIME-based pipeline, continuous speech separation-based pipeline, speaker beam-based pipeline, and the recursive selective attentional network-based pipeline. So those 4 pipelines are all published, but they all have the capability to process the conversation transcription in an end-to-end manner, which means they can take the very long form of audio, in this case 10 minutes, and generating a speaker attributed transcription, like A speak this at 4 seconds or something like that. So I will briefly introduce each one of them, and then I will move to the actual working plan. So what are we going to do on top of the baseline? So we start from the CHIME baseline here. The CHIME baseline is a baseline system that is made for CHIME 6 challenge. So we adapted from the CHIME dataset to the LibreCSS dataset. So this pipeline is actually very standard pipeline for this type of conversation transcription. So it has a speech diarization module, speech recognition module, but each of those modules has a single active speaker assumption. So that means it will just tend to ignore the overlap region. So this serves as our starting point. So this is basically the best system we can get with without multi-talker processing. And the several state-of-the-art derivation system and the speech recognition system on LibreSpeech was used, and we get a series of results here. We can see here. So with Oracle derivation, we can see the impact of the overlap on the speech recognition. So if we can see, if we have a 0% overlap, the order rate is like 3 with end-to-end model and 9 with a hybrid model. And then when we go to 40, it's like 10 times bigger, and for this one is like almost 4 times bigger. So that was the overlap part for the overlap interference to the ASR, single speaker ASR. And then if we compare the Oracle derivation with spectral clustering, we can still see a very big significant drop. So that will basically the show reflects the how much the overlap speech will affect the speech derivation. So this one is finished. So we have a series of the benchmark. Then we will start from this. The second pipeline is a continuous speech separation pipeline. So this pipeline was found by Microsoft researchers to be effective in the meeting transcription. So on top of the CHIME pipelines, the main change is that they have the speech separation handling capability. So the system, the long form of audio will first be processed by this continuous speech separation module, which separates the input stream into a fixed number of output streams. So in this case, 2, assuming that corresponds to the maximum overlapped speech number. So that we basically in this pipeline, they only contains 2-speaker mixture. So the number of output is always 2. Then after this unmix, after this CSS module unmix the input stream into 2, then they perform ASR, segmentation, diarization, and then they merge the 2 channel into the final result. So this pipeline is also done, and we can observe a significant improvement from a CHIME pipeline, which is 30% to the 21.7%. So this shows the capability of speech separation. Although this is only a starting point, we can see it has promising results. And then this pipeline is implemented to generalizable to different speech separation technology. So because continuous speech separation is just a very simple mechanism to glue the local processing, like utterance processing of speech separation, to the long form of recording. So they can be generated to the longer audio processing. And the people working on this pipeline were starting from the results here to further improve during the workshop. And then the third one and the fourth one are basically invented from the NTT researchers, which it refers as a stream separation and extraction. So that is similar to the continuous speech separation, except this stream separation takes the speaker embeddings as the glue. In the continuous speech separation mechanism, they use the shared part from overlap window, but here is using speaker embedding. So they have a different speaker embedding. It can be extracted from the enrollment speaker, or it can be extracted from same meeting. Then given the enrollment speaker and the mixture, so they extract a certain speaker out of the meeting. So therefore, the number of outputs here corresponds to the total number of speakers in the meeting. That is another difference between the CSS pipeline, which has a fixed number. So the number of output in CSS pipeline corresponds to the number of overlapping speech, but here is the number of actual participating speech. And then there's also pipeline. So this is still being made, but after the workshop, we will have all the benchmarking results for all the baseline and improvement will be open sourced. And the last one is similar to the target speech extraction, except the speaker embedding is extracted within the meeting. So they explore a iterative separation mechanism to extract one target speaker at a time. Then they move from block to block. So given these 4 pipelines, so we have a very good starting point. So we have a target here. The minimum target is that we're just building and open sourcing the platform for the unsegmented audio speech transcription and derivation. Consists of multiple state-of-art pipelines. We just build a platform and allows people to compare the pros and cons of each pipeline with respect to different application scenarios. And they allow other people to incorporate their work into some of pipelines. So they can not only see the improvement for their modularized design, but they can also see how much that improvement can convert to the more practical setup. So this is the minimum contribution we want to make. So on top of that, so we are also forming sub-teams to improve different aspects of the problem. I will introduce slightly later. And then we want to develop new technologies and bring new insights to this bigger picture. So as mentioned, we have the sub-team strategy. So we've currently, from this several rounds of discussion, we have formed the sixth team, which is focusing on the pipeline updating, long sequence modeling, E2E, end-to-end ASR for multi-talker, unsupervised separation, uncertainty modeling, and all neural diarization and extraction. I will briefly introduce the status and the ideas. I will not go to details because this is a lot of them has not been verified. We just think they will work, but we will, at the end of the workshop, we will give a very detailed updates on each aspect. So before the actual item, the first team will focus on the improving the pipeline. So because there's we have a very large group, each of group has some work that's previous published existing work that has some relation with at least one of the pipeline. So this team will basically focusing on bringing those state-of-art method to this pipeline to get in the systematic comparison on the same platform. So we will better understand the pros and the cons, because of course each system will have a different emphasis. Some of them will emphasize on the online processing, some of them will emphasize some other applications. So we have a better understanding. And also meanwhile, we are also trying to explore the room acoustic simulation, because that is on top of all the modularized updates, because everything nowadays we're all working on a deep learning based method. So we need a data to handle that. So from this meeting, our full-time member Jun Jundu and Shinji will be the point of contact, and Takuya will help for the acoustic simulation part. And then for the E2E multi-talker speech recognition, there's two directions to explore. So the first direction is trying to use a multi-pass, trying to explore a multi-pass strategy to improve the overall performance from the diarization and the ASR. So usually, for example, for the CHIME pipeline, so currently it's a one pass, they do the diarization and do ASR. Clearly, if after the ASR they do diarization again, then do ASR, there be more possibilities. So that's one thing, and this thing can be formed into the end-to-end framework. So that's the first thing this team is trying to explore. The second thing is that is trying to build new model using additional information, auxiliary information. For example, some team member showed that in their previous work, the context information would be very useful especially for the multi-talker scenario for end-to-end speech recognition, so that people can further extend that into this fit that piece of work into the bigger scope. So that's another direction, initial direction to explore here. And this team will be led by Shinji, Mark, Cascade, and me. We will basically be the point of contact, and I will show a table for how they split the effort. And the second direction is that the long sequence modeling. So as mentioned, most of the work is nowadays on separation or ASR have this short window modeling. So they have utterance-wise modeling. So they have a small 4 seconds or like one utterance. So then in this subteam, we are trying to have a build model directly on the long form. So of course, we can easily imagine could be different challenges, such as memory, or or simply a long form of audio. So we have some ideas and observations and hints showing they might work. So for example, we plan to start with 2 directions. The first direction is that we have a short window processing, and we have a shared memory pool. So in the bottom layers, we have each of the local processing contribute to the memory pool, and which will be used in the upper layers. So for example, intuitively, we can the effect could be during the meeting, some part of the target speaker is not overlapped. So the non-overlap, the speaker can help provide some hint for the system to extract the overlap region for that person. So we hope to build a long sequence modeling to leverage this information. And of course, there are other ideas. For example, we can have this DPRN style, dual pass RN, which is a work for the time domain processing, but we can also use a similar idea to directly model the multi-dimension structural input from the long form of audio by multi-direction LSTM. So there are a bunch of ideas. So this is another team, and this team point of contact will be me, and with some students here. And then we have the all neural modeling team, and this team will focus on the extension for the third and fourth pipeline, which is a speaker beam-based pipeline and the recursive speech separation-based pipeline. And they are trying to address the existing problem of streaming separation streaming separation and extraction, in the tracking speaker in the long meetings, and scalability on the speaker numbers and the silent speaker handling. And by doing that, they plan to start with using external memory here. So we can see a lot of team has very much shared information. So although with different emphasis, so we can easily imagine there will be a lot of interactions between across the different meetings, but this will be our starting point. And then the team of this team will be, the point of contact team will for sure will be Cascade and Mark from NTT. And then we will move to the unsupervised source separation and diarization. So this team will be led by Hakan and Zhang, and from Google. And recently they released a benchmark showing that, and the algorithm showing that they can do the speech multi-source handling by the unsupervised method, which can achieve very good, similar to the supervised learning. So this is actually very promising because for the real meeting data, the clean source is usually not available. So if there's a unsupervised learning mechanism, so for sure they will be helpful to the a lot of different areas, including the separation and the diarization. So this is actually a very promising direction that will be mainly led by Hakan and Zhang. And then there's a team which will focus on modeling the speaker embedding uncertainties in the neural network. So they have a previous work in adding the speaker embedding uncertainty by and use that into diarization. They show that it has very promising results. For that work, they mainly consider the single speaker region. But here, when they move forward, they very easily to imagine that for the multi-talker scenario, the uncertainty is even more useful because the separated speech usually contains the interference and distortions that will be hindering the lots of modules, not only from the speech recognition, but also from diarization. So a uncertainty modeling on top of that will be intuitively, it will be very promising to fix a lot of this issue. So this team will be led by Johan and Nico from Amelia and the BOT. So we have an initial team up here, and we can see we have 6 teams, and each team is associated with from 1 to 4 students. So roughly we have actually very balanced teams formation. And this is only for the full-time member. And because of the lower efficiency of the communication, this year we decide to let the part-time people to directly connect to the POC of the projects, so they can directly associate with that. Then the POC will arrange the contribution and the connection with part-time people, because the part-time people have a different might have a various time availability and starting time. So we will just have the point of contact of a full-time member for each team to handle that. And meanwhile, we still want to keep, although it's virtual, we still want to keep the spirit of workshop. So we would like to create an inclusive, transparent, and fair platform to allow people from different backgrounds who cannot usually work together. For example, I'm from Microsoft. I want to work with the people from Google and NTT for a very long time. I really don't have this opportunity. So for this workshop, we would like to create this platform for everybody from a different background to share and collaborate on the one problem which everybody is interested on. And also we can observe, it's actually very exciting that we observed, especially as time goes by, it's approaching to the beginning, we observe that there's a more connection forming every day. So we really hope that we will end up with a lot of chemical effects between the teams and the members, between the students and researchers. So it's very, very exciting to see those are forming every day. And that will be all of my introduction. Thank you very much. I think I go slightly faster. We have 4 minutes left. Maybe we can have more time for questions.
Yes, Joe, that was nicely done. Thank you. Well, we can maybe do a virtual clap.
Thank you.
Yeah. Okay, so the floor is open for questions to the entire audience.
Oh, I don't think I can hear you.
Yeah.
I will stop sharing.
Okay, so I think all the panelists who turned on their cameras are visible to people. So questions from the floor, anyone? Maybe from Ivan or from some of the...
If there's an anonymous Q&A.
Okay, so go ahead, Desh, read it and let people answer it.
It says, are there any plans to use real meetings versus synthesized recordings?
Yeah. So this is, we know that, so the LibreCSS data set actually is good in some aspect, but also bad for other aspects. So it's good because they have a detailed design of the overlap ratio, and also because they use the Libre speech. So a lot of speech recognition work is using that as benchmark. So a lot of them can be directly ported here. But the bad part is that it is simulated. So it's really recorded, but it's fake. It's not like human interaction, because especially for the multi-channel recording, when we talk, we actually move hand. So that will cause some disturbance in this sound source localization. So we want to use that for development and benchmarking. And after we have some initial result, we also plan to apply the findings on other data sets, such as the DeepCo, XE, meeting corpus, and AMI data set, and CHIME, sorry. Yeah.
Okay. Great. There's another question from, it's a comment from Thomas Schaaf. Thomas Schaaf says, FYI, the verb mobile data has speaker overlap annotated.
Oh, thank you. So yeah, those are the real. So the good part for those real data is that this is real, right? And also they have a, but the limitation for those is that usually it's, especially for analysis, is sometimes have a, so because it's real, we can't really control the ratio. So again, I think once we have some initial results, so LibreCSS actually sits in between of the purely fake data, that is simulated data that's being used in many of the works, and the purely real data. So we believe this is good for development. So after this, we will definitely, I mean, even without saying, I'm pretty sure people from different projects will use, because the reviewer will give them a hard time if they only use that. So they will definitely use other data set for evaluation.
Okay. Thomas has a follow-up. How do you define or measure WER for speaker overlap? Since he just asked, I'll follow with his question first.
Yeah.
So how do you define or measure WER?
So we actually use the similar strategy as CHIME. Maybe Dash is better person to have to answer this question.
Yeah. Okay. So what we have is what we call concatenated minimum permutation word error rate. So it's kind of speaker aware word error rate. So what we do is you have a reference text which has speaker labels, and with the diarization and the ASR system, you also create a hypothesis which has the text as well as the speaker labels for that. But the speaker labels may not directly correspond to what you have in the reference. So what we do is we find the permutation between the speaker labels in the reference and hypothesis, which minimizes the word rate, and we report that, which we call CPWER. I hope that answers your question.
Yeah. So a quick housekeeping announcement. I saw a couple of blue hands go up in the participants, but they went away quickly. So just so people know, if you click that hand twice, I think it raises and then lowers it. It's like a toggle. So if you meant to raise your hand and you don't see a blue hand, you should click it again so that I see you, because I saw them come up and disappear quickly. So please feel free. And also, if people want to ask their question verbally, I'm happy to enable their audio, so they should raise their hand for that as well. So that's that. So there is another question, Joe. This is again anonymous. It says, can you explain a bit more about how to compute better embeddings?
Clearly, this question is for Nico, right?
Yeah, Nico?
Okay, thank you, Sue. I'll just say a few words about what an embedding is, and then I'll say what a better embedding is. In machine learning, embeddings can be used for words or sentences or images or speech input. These input spaces are complex to model. Words are discrete things, sentences are very complex discrete things. Images and audio signals are also very complex. So if you have some pre-processing, it's essentially a kind of a feature extractor. It takes a whole input, put a whole image or a whole cut of a recording, and it outputs a single vector in Euclidean space, in R to the n, where n is maybe 100, maybe 500, something like that. So if we're interested in a problem like speaker diarization, which is one of the forms of speaker recognition, then we want these embeddings, which are points in Euclidean space, for the same speaker to be close and for different speakers to be far away. And then we can use relatively simple algorithms to do things like diarization. So that's more or less the state of the art. That's what an embedding is. So how do we get a better embedding? So unfortunately, real life is a little bit more complex than that. So you can get different quality of input. So if you're talking about speech recordings, you can have shorter or longer recordings. And obviously for a longer recording, it's easier to tell who the speaker is. Or it can be noisy or clean speech. Again, the clean speech is easier to tell which speaker is speaking there. Also, there are things like sampling rate. The higher the sampling rate, the better the quality. So with varying quality, you cannot have the two embeddings exactly in the same place. So if there's a bad quality, the embedding is essentially, it has to be distributed. You're not quite sure where the embedding is in embedding space. And one should be able to use that information. If you're just extracting a single point embedding for each input, then you are essentially throwing away that quality information, and you can't propagate that quality information through into your final output. So we've been working for a few years already on a concept of what we call a probabilistic embedding. So the embedding is a distribution in embedding space rather than just a point. And we do it all probabilistically. So we like to model the embedding as a hidden variable, and then we do an inference, a posterior distribution on where that hidden variable might be given the input. And then you marginalize over that hidden variable to get your final answer. So I think that's enough for now.
Okay. So Nico, if I had to amplify or elaborate, are you thinking something like normally when we build an X-vector extractor or train an X-vector extractor, we sort of do data augmentation, take a speaker's clean recordings and add noise and do this and that, just so that the hidden layer gets noise injected into it, but then you backpropagate and hope that you can push the representation back to the same place, and that becomes your extractor. What you're saying is don't throw away that information about where the noisy version was relative to the clean one. Instead, build a second part of the embedding which characterizes that distribution of that clean X vector, meaning around the clean one, where is the noisy one? Is that the kind of thing you're thinking?
Yes, yes, that's a good summary. So In practice, what we're going to do is we're going to add on another part to the embedding extractor, which will extract a representation of the uncertainty. So if the embedding is, say, 100-dimensional, if you were working with Gaussian uncertainty, then you could have a 100 by 100 covariance matrix representing that uncertainty, but that's a little bit heavy to work with. So at the moment, we're working with a diagonal representation of the covariance. So for every component of the embedding that we extract an associated variance or precision. So the precision is just the inverse of the variance, and the precision has the nice interpretation also that it can be seen as a quality factor. So the higher the precision, the higher the quality of that particular component of the embedding. We're not representing the quality of the embedding with a single scalar. It's good or bad. If you think of, for example, telephone bandwidth speech, some of the fricatives get cut off. So if you have an embedding and you can imagine that some parts of the embedding have the fricatives and others have the vowels, then in telephone speech, we should be seeing the fricatives have smaller precisions than the vowels. So the vector valued precision allows you to drill down to that level of detail. Also, the precision can be seen as an attention mechanism. So if you're extracting a sequence of embeddings before you're going to do diarization across that sequence, then the precisions can if the precision is 0 or close to 0, then it effectively removes those embeddings which come from bad little parts of the conversation, maybe from the badly overlapped or noisy parts, and then they can be ignored and won't spoil the whole diarization.
Okay, there are no pending questions in the Q&A box. Anyone from the floor? Please.
I have a question.
Go ahead, Najim.
So this is more for the whole team. You guys split the topic, in several sub-projects, and you describe you have great teams great members for each teams. But how you combine all the modules to create one final system? I didn't see that maybe I missed it from the presentation, but I didn't see there's any strategy that you guys working to unify everything and make one single system that compare at least to much of the models?
So, Joe,
Najib, can I answer?
Yes.
Nobody is paying us to produce a
No, not that. Like you make it.
We want to do research, so if we can publish a number of papers, we're happy.
Yeah. No, so I think Joe's link seems to be frozen. I'm not sure, he's not. So, but I think that Najim's question is more about how to bring all the sub-teams together so that you're focused on a unified effort benefiting from each other. I think that's the real question.
Yes, I can actually answer it for Jules. She seems to have some communication problem. We actually are caring about this kind of issue. And what we did first was, as Joe mentioned briefly, but we actually made a Cardi style, the pipeline based the script, which do everything and which is modularized. For example, if we have a better embedding technique which can be used for the speaker diarization, we just care about the I/O of the file, and then we can just replace the speaker embedding module to the better one. Similarly to the speech separation SR part, we basically make it as a kind of generalized to use such kind of the batch script style glue-based approaches, again, based on the Kaldi style, so that we can easily integrate each the modules update by using this kind of the techniques. And we also actually have a big table. If, for example, the component B is changed, we compute all for our kind of metric, like a diarization metric, word metric, so that separation of the technique A and B can be easily compared and so on. However, there is some challenge. For example, some of the techniques we propose, we try to proceed entities method or end-to-end method, which does not completely fit to such kind of a modularized framework. So how to kind of combine this the modularized framework with our end-to-end approach is an interesting but challenging problem. So which we will also try to work on it. But basically, yes, we are really caring about this kind of integration issues.
Okay. Shinji and Joe, is Joe back? No, not yet. So there is a question from Ivan.
Joe has issue with his internet. He just write it in the chat.
Great. Okay, so Joe will answer in the chat if need be, and one of us can read it. So basically, Ivan Medenikov asks, are we going to use the target speaker VAD approach that they presented in the CHIME challenge? And I was going to ask you the same question, actually. So can you say a bit more? Yeah, okay, go ahead, answer that. Are you going to use it? What is the plan? How are you going to modify it?
Yes, first, I would like to mention some of them may not know this kind of techniques. Target speaker VAD is a one way of using combining a speaker extraction and diarization, and having a significant improvement in the CHIME 6 challenge, which is actually one of the best champion system in the previous CHIME challenge. And our answer is yes, we really would like to use this kind of technique. And several proposals, not only for the embedding and diarization team, but many other teams are actually interested in target speaker, speech separation, extraction, and recognition. And we are definitely thinking of, or actually try to use TSVAD technique as a kind of a powerful state-of-the-art technique.
Okay. Ivan, I hope that answers your question. If not, just repeat it or ask a follow-on. In the meantime, there's another question from an anonymous attendee. How is speech separation going to be included in your pipeline? Is it supposed to replace diarization?
Probably Desh, could you answer, because you recently finished the CSS pipeline that actually also have a great benefit.
Yeah. So if you have a perfect separation system, which if there are 8 speakers in the meeting, it separates the audio stream into 8 parts, then of course you don't need diarization. But what we have in different, like with Joe's CSS separation is it divides the whole, since there are only at most 2 speakers overlap, it divides the whole audio stream into 2 streams. Which are but there could still be possibilities that the same speaker exists in both the streams at different times. So you still need a diarization system even after you have separated it. So you have separated the audio itself, but it still won't tell you which speaker it's speaking in which parts of the audio streams.
Hopefully that answers your question. There is one more. Is there a focus on online meeting transcription over offline approaches? Is there a difference between online versus offline? What are you guys focusing on?
Yes, for now, we are focusing on the offline, but definitely, for example, Microsoft CSS, the pipeline is designed for the online processing. So we could definitely also consider to extend it to the online processing. But for now, in the main kind of the workshop, we are focusing on offline processing.
Okay. And so, by the way, just so the audience knows, Joe is having difficulty connecting back. So he's signaling us on the side saying, hey, please continue and he'll try to fix his internet connection. Okay, so that takes care of that, and we're also out of time. So again, let's thank Joe and all his team members for a good presentation and Q&A. And let's move right along. And let me introduce our next, actually, Najim, do you want to introduce Alex and take over from here?